So welcome. So we're going to do a 3-chapter sequence on solids, liquids and gases, and this is one on solids. And we're going to talk about the structure of solids, and we're going to find that the properties of the solid depend upon their structure. There's people who spend their entire lives looking at how the atoms stick together and what patterns they form. And you might take a substance like, for instance, aluminum, and depending upon how it's processed, depending upon whether it forms big crystals or small crystals and the like, you'll find that they'll have very different properties. The property is almost not so much about the stuff, it's about how the stuff is put together in terms of its crystallinity. So what we say is solids are either crystalline, that means there's a regular order of atoms, or amorphous. Amorphous means you have the same number of atoms, but they've not got this regular periodic array to them. They're kind of just thrown into a bucket and they join together, they bond. It's not like they're not bonded, but they're not bonded directionally. There's not this like beautiful repeating pattern that you get in crystals. So metals, salts, like literally like sodium chloride, and most minerals, iron ore, that like a crystalline. And you can see that if you go into geology and you dig out some of these substances, they'll tend to break in straight lines. They won't come out as a ball. They'll tend to break in a straight line. And what that means is there's some kind of crystalline structure there. It's not perfect necessarily, although it can be. If you look at sol under a microscope, you see these cubes. It's literally a cube of stuff that we put onto our food. So, and that's because the outside form is reflecting the inside structure. And as I say, there's people and they just get immersed in that analysis. My old boss told me that if you took all the material that had ever been analyzed using electron beam structural analysis, which is what you use to get this, it would be less than the end of your thumb in the entire world forever. Less than the end of your thumb. And yet, from that small amount of material, in tiny samples, we've improved materials so that our cars are half as heavy as they used to be, twice as strong. They got much better thermal situations so that they don't expand and leak. The materials revolution is just amazing over the last, I'd say, 40 years. Unrecognizable materials. When I was a kid, plastic was Bakelite. It was brittle. It basically was like, to try to make it look like wood, and it was pretty, you know, it just was the way it was. As all my kids all my toys when I was a kid were made out of Bakelite. You stood on it, you broke it. And you compare that with just how many variety of plastics we have these days. It's like, and that's just all materials research. And that's looking at the structure of solids and saying, why is this got these properties? Oh, look, it's got this grain structure, this crystalline structure, this amorphous structure. And then learning how to manipulate those things. So some metals, in fact most metals that are useful are polycrystalline. Not mean to say they have different materials. Same stuff, just broken up into different directionalities. If you look at sometimes if you get a solar cell on top of your calculator, have you ever seen the calculators where they come and they don't need batteries, they just have a solar cell on top? If you look at that, it's often purple, and it's often got different patterns of purple, dark purple and light purple and dark purple and light purple. And there you're looking at the different grains of the silicon. Rather than trying to make single crystal silicon like you would do for your computer, where you pour it into this thing very slowly and you actually spin it out of the liquid. When you're making polycrystalline stuff, you have a graphite bucket and you kind of pour it in, and the bucket's warm, but it's not perfectly warm, and you kind of process it a bit, but you're not going to get a big single crystal. You're going to get a whole bunch of smaller crystals, and they work. You lose a little bit of efficiency around the edges of the grain, but that's not the end of the world. And some materials, like if you want to make a very fine, flexible sword, What the ancients discovered was how you did that, and that was because you beat the sword and you quenched it and you put it back in the fire, and you beat it and you quenched it and you put it back in the fire, and you folded the metal on top of itself and beat it, and you did that for a couple of days, and then you had this really flexible sword that could be really sharp. And for instance, in the Middle East and in Asia, they had those swords quite early on. And in Britain, they didn't have that processing, so they would make big, heavy, clunky swords. And if you missed and hit the tree, your sword shattered because it had very poor properties. It was a bludgeon rather than a blade. And that was because they didn't know about this processing. Did the ancients really know? Damascus was famous for swords. Did they know what they were doing? No, they just knew that this worked. And they learned the recipe. And years later, I mean, in this last century, people did the microstructural analysis and figured out, oh, this is micrograin, not just polycrystalline, but micrograin. And that's what gives it some of its flexibility and the like. Very, very, really quite amazing stuff. And don't think, so it's tempting to think, oh, science got rid of all these recipes. And so one of my friends was telling me about, and he worked for basically the Defense Department, and they were putting up military satellites. And the military satellites needed what they called an emitter. It was basically a source of electrons that would cause the satellite signal processing to work properly. And they would make them out of some very exotic materials. And they found that they'd make them and test them and make them and test them, and then they'd have like 100 of them, and they'd ship them to the various manufacturers, you know. And suddenly they found they couldn't get any surpass quality assurance. They were like failing. And the management was kind of like, what's going on here, you know? And it turned out that Joe, this guy who'd been there for like 50 years, retired. And his job was mixing this stuff together, this like really kind of low-tech job, mixing the powders together that were then sprayed onto these emitters. He'd retired. And when he retired, these things stopped working. So they said to the guy who replaced him, didn't Joe train you? He goes, yeah, I twiddled it, and he just couldn't get it. And he's like, it can't be that hard. So they asked Joe to come back to kind of like train again. And Joe comes back and he says basically, show me what you do. And the guy's doing it. He goes, oh, no. Too hard. Like that. And Joe had all these, he'd learned over a long time just how to get better products. And you know, have you ever made bread? The first loaf you make looks like a rock, and then you follow the recipe, but by the end you're making these beautiful loaves that just like they smell, and you cut them, and could you write down the difference in what you did? I'm not even sure that I know the difference in what I did, but by the end of my baking, I was making much better loaves than before. So it's not that science means there's no art. There is. Science would like to quantify so that it wasn't as much art, but it's not that that science has replaced all the art. There's still experience, and the intangibles, which are always hard. In 1912, a guy called Max von Laue used X-rays to study atomic structure in crystals. That was a big breakthrough. He used these new things called X-rays. They didn't really know what they were. All they knew was when they fired electrons at a metal, it kind of gave off this invisible ray that made film go black. And how did they find that out? Completely by accident. It was just one of those things. And then they shone them through people, and they said, look, we can see the bones. And they didn't know enough about dosage, so they did massive doses, and people would move around and eat things, and you could watch the stuff go down their throat. There was a classic one of, if you ever eaten something and got a piece of bone in there, you stop biting really quickly, and they want to know why. So they'd give these subjects ball bearings, just put a ball bearing in a sandwich or something, and they'd they'd film them as they were chewing on this thing, and it turns out your teeth are like little springs, that they're very sensitive to pressure. And if there's too much pressure, there's this auto reflex which just stops your jaw from from moving, or else you'd just smash your teeth to pieces. So they were very curious about that, and they did all that live. You know, the people probably had a fair amount of sickness in older age, but they just did it because they didn't really know. And then to shine them through metals, and if they did it just right, they could see this like very curious pattern. And they figured out that was the diffraction pattern for the metals. Later, William Bragg and his son William Bragg developed the math to interpret the Laue patterns. And you could work out atomic spacing, how far the atoms were apart using this stuff. It's really quite impressive. The key thing about crystalline materials is that they have a regular ordered lattice. It's like scaffolding. And sometimes it's like a cube, and sometimes it's like a tetrahedron, like, you know, 3 on the bottom and 1 on the top. Sometimes it's like that, and it repeats, makes it very strong. And if it's cubic, you can cleave it at 90 degrees. If it's tetrahedron, you can't. You've got different symmetries. And when they get a big diamond and they make it into jewelry, that jeweler is very skilled at recognizing the planes at which that diamond will cleave and just hitting it with enough force to make it cleave. They don't grind out that facet on a diamond ring. They cleave that facet on a diamond ring because they know the repeating pattern of the atoms. It's really quite, as I say, really quite amazing. But, you know, they only get you so far. There's ample space for other types of materials, and rubber and glass and plastic are all amorphous materials. They're just a hodgepodge of atoms thrown into the bucket together. They form bonds to each other, so it's not like they're not like a liquid that can just flow past each other. But they're not like a crystalline material, which is really quite rigid. You can bend plastics much easier. Some plastics you can bend a lot. Other plastics not necessarily so much. You can get some of these things to flow. The classic one actually is glass. If you put a piece of glass half over the edge of a table, and you come back in 50 years, it will be deformed. On the bit that wasn't supported, it will tend to. And you see that sometimes with old glass tends to get distorted. It's some thicker at the bottom because it kind of flowed. So it's not really, we can sometimes refer to it as a supercooled fluid. It's kind of solid, but the atoms don't really have a regular position to each other. And it's like a room where people are just jumbled in there. If they're all sat in desks, you know exactly where somebody should be, and if they're out of place, it's obvious. But if they're just jumbled in there, then if I move relative to you, it doesn't make that much difference. So in a way, that's annoying, but in a way, that's incredibly useful. I mean, it's kind of like these things form a very useful purpose. Because they tend to be a little bit easier to make, sometimes amorphous materials are kind of considered as being second-rate. Amorphous silicon is cheaper to make than polycrystalline silicon, which is cheaper to make than single crystal silicon. So single crystal is like the wonderful stuff, but they're all useful. They're all. It might be cheaper to make, but it's got different jobs it can do. So we say they're amorphous solids because these in these materials, the atoms and molecules are distributed randomly. In many amorphous solids, particles can move. For example, rubber is elastic and glass flows. Whether crystalline or amorphous, the atoms in a solid vibrate about their position. They've got energy, so they've got to vibrate. The atomic bond fixes the atom in position. Some solid properties are a direct result of the type of bond holding the atom in place. And there's several types of bond. There's basically ionic, which is I'll give you an electron because you need an electron. I'm positive you're negative, would be attracted. To covalent, where basically I need an extra electron, you need an extra electron. I'll give you a share of mine, you give me a share of yours, which is very directional. So you tend to find that covalent materials tend to be really quite rigid, and you can't work them with a hammer. You can't make them thin by hammering them. They'll shatter. A plate. Well, plate's amorphous as well. But anyway, no, that's a good example. No, it's got covalent bonds. A plate, you hit it, it shatters. Whereas with for example, with a polycrystalline material like a metal plate, you can hit it, you can beat it, you can bend it. It's still solid. It's still maybe hard to bend, but you can stretch it and you can bend it. It's what we call ductile. And that's because the bonds in the metal, they don't care what direction. If you force it, I'll point over there as well as over there. Whereas in the ceramic, it's like you're going to be there or nowhere. If you're not in that direction, I'm not going to bond with you because I've got to go in certain directions. So it makes it the material's properties come from the microstructure. Okay, so amorphous and crystalline, and they're both valuable. Crystalline has a regular repeating pattern. Amorphous tends not to have that. Crystalline materials tend not to flow. Amorphous tends to flow. That leads us on to density, because sometimes we want to characterize things in terms of density. And so basically we have density, and there's two types of density. There's, if you like, and there's a mistake. I'm so sorry about that. This is mass density. And this is weight density. So mass density is your mass over the volume, and your weight density is your weight over the volume. And the mass over the volume is the mass over the volume. And the weight density, well, the weight is the mass times the gravitational field strength divided by the volume. So, lead, 11,000 kilograms in 1 cubic meter. I weigh 80 kilograms. That's a typical adult. Weighs 80 kilograms. So 11,000 kilograms in a 3 by 3 by 3 block is really heavy. But it's not the most heavy thing by far. If you've ever heard them talk about depleted uranium, they talk about it with the army and stuff like that, munitions. It's basically uranium which is not radioactive. And why do they care about it? Because it's really dense. 19,000, 20,000 kilograms per cubic meter. It's really dense. And there's something even beyond it, which is osmium, which is really an unusual element. That's 22,000 kilograms per cubic meter. So you can get some really big densities. You can get mercury. Mercury is quite dense. Water's like, if you like, the standard. And that's 1,000 kilograms per cubic meter. We're 97% water, so. And ice expands when it forms. So it occupies more volume. Same number of molecules occupy more volume. So ice is actually less dense than water. So the one I remember water. And I kind of remember that there's a whole bunch of things that are denser than that. Certainly I remember lead is denser than that. And other things are lighter than that. So when water freezes, it expands. What does this say about the density of ice? That the density increases, the density stays the same, or the density decreases? What do you think? So water expands when you freeze it. So same number of atoms occupy a bigger volume. That's what expansion is. So what do you think that does to the density? So what does this say about the density of ice? So in becoming ice, does the density increase? Does the density decrease? Does it stay the same? So what do you think? We're about 11 people. Let's go. So in going from water to ice, does the density increase? Does the density decrease? Or does it stay the same? We're about there, aren't we? Let's stop it. Anybody else want to? Okay. Mainly people saying C. Let's have a look. So let's look at it. So C, density decreases. Yeah, same amount of stuff same mass, occupying a bigger volume means the density decreases, and also the fact that ice will float on water means that the density is decreased. So yeah, density decrease is good. Which weighs more, a litre of ice or a litre of water? I'll do this one. Which weighs more, a litre of ice or a litre of water? Well, let's have a look. I've got the same volume now. This one's full of water. This one's full of ice. Ice is less dense. If density equals mass over volume, or if I like weight density equals mg over volume, mg is equal to the density times the volume. Oh, look, the volume's the same. It's only the density I'm changing. Which one has the bigger density? The water has the bigger density. So, which weighs more? A litre of water. If you like, I was a litre of water, and then you froze me, so now I expanded, and you cut off the stuff that stuck out the top of the litre. I lost some of my mass. If I lose some of my mass, I can't weigh as much as the water. So either way. And then another property is elasticity. Elasticity is stretchiness, if you like. Elasticity is the property of changing shape when a deforming force acts on an object and returning to the original shape when the deforming force is removed. So I get a wire and I stretch it, I let it go and it comes back. Rubber band, stretch it, let it go, it comes back. If I get a ruler and I press down on it, I stretch it, I stretch the top and compress the bottom, let it go, it comes back. Materials that do not resume their original shape after being deformed are said to be inelastic, not elastic. So a spring is a classic case of an elastic material. Elastic structure, let's say. It's great. It's a piece of metal that goes round and round and round and round and round, and you can make it expand or compress. Springs and many wires, for example. It doesn't have to be coiled, but springs and a whole bunch of stuff obeys a thing called Hooke's law. Hooke was a contemporary of Newton. Hooke was 7 years older than Newton. When Newton was an undergraduate, Hooke was like that 20-something guy that was like very successful. He got very successful very early. Newton really admired him. Hooke was a smart guy. Hooke basically was connected pretty well. And he and a bunch of other connected scientists went to the king in Britain, they were English, and said, look, there's this thing called science. It's going to replace a whole bunch of superstition. It's based on evidence, evidence-based science. Like, you know, we talk about evidence-based business and evidence-based education. And why don't you give us some money? We'll do it. And the king said, sure, because he was dead keen on science. So they formed the Royal Society, which is still in existence today, about 350 years later. It's still in existence today. The printing press had just been invented, so they printed journals. So the idea is you do your research, and rather than just sending letters out to your buddies, you send it into the Royal Society, and we print it. Well, first thing we do is send it out to other people, and we say, what do you think? And if you get the thumbs up, we print it and we send it out. If you don't get the thumbs up, we'll send it back and say, hey, look, you know, here's some ideas, you know, improve it. And it's the method used to this day. There's a whole bunch more journals, but that's the method used to this day. It's slow, it's tedious, but hey, you know, we've got the rest of eternity to get things right. You know, let's take our time. Newton was like, he was so keen. So he was the guy who pushed himself in the eye with a needle to see what would happen. And he saw colours, so he reckoned that light colour was due to the pressure of light on your eye.
Who was the artist that like cut off the lens in his eye so he could see ultraviolet light?
No.
He painted his backyard and then he cut off the lens of his eye and then he saw like ultraviolet by the light, and he painted it again, and you can see the painting. It's all purple and blue.
Really?
Spectrums.
Oh, can you find out and let me know, because I have no idea. That was amazing. I didn't know about that.
The painting's really cool.
I'm sure it is. So he went to the. So he did this. So he turns around to young Newton and says, "Hey, let's do it." Newton says, "Great." He sends in a paper. Hooke sends it to some of his buddies who are old guys set in their ways. They don't know as much as they think they know. They chew it up. This is nonsense. They hadn't done an experiment in their life, probably. They just know what's in the books. This is nonsense. This can't be right. Newton is so angry. And who does he remember? Is it the old guy that he didn't expect anything more from them? It was his buddy, his hero, Hooke, who led him on. So Newton did not submit any more papers. That's why Newton wrote books. He had like 3 books. And he waited until he knew it all in his mind, and then said, let them argue with that, All right, you're going to pick it. You can argue with, I'm going to have a tome. You're going to have your opinions. So they were like amazing books. But he never forgave Hooke. And because he was 7 years younger than Hooke, it kind of like, because he was like really, really sharp, Hooke would try to make up with him. And Newton would like have none of it. Hooke wrote a letter to Newton saying, look, you've done so much. You've made the science progress so much. Please be more involved with the society. And Newton was going, Newton wrote a letter back saying, no. It's nice of you to say that. But if I can see further than anybody else, it's because I've stood on the shoulders of giants. And it turns out that Newton is a very tall man. And Hooke, 5'6". So is that a robe? Is that like a snob? Is that Newton really sticking the knife in again? And then finally, Hooke either, I don't know if he died or retired, but basically was less powerful, and Newton came in and took over the Royal Society and kind of erased him. He kind of, Hooke's left with this law, and he was an active scientist throughout his life, and he was. If you look, you find Hooke's comments on motion and Hooke's comments on this, and Newton came in, and Newton was he was a superior scientist to pretty well anybody at that time. So maybe it was inevitable, but there's also this sense of, he just kind of like said, people will forget about you. I am just going to bury you, So poor old Hooke is left with this little bit. So I always feel like, you got to give him his due. It's very valuable. What it says is that when you stretch a spring, how when you stretch a spring it pulls back? That's a restoring force. And the restoring force simply depends upon the stiffness of the spring. That's what that is. If it's a stiff spring, it's got a bigger number. If it's a weaker spring, it's got a smaller number. And how much you stretch it. And that is not, well, it is a common force, but it's not the way all forces work. For example, if you go into space, then as you go twice as far away, well, there's our twice as far away, the force is a quarter as big. It gets less, and it's non-linear. Whereas this one, if you go twice as far away, it's twice as strong. So it's kind of like the different forces behave in different ways. This is the way springs behave. It's the way the atoms behave when they're in a solid. If you stretch a spring and it comes back, it's obeying Hooke's law. You take the force away, you take the displacement away. So it's kind of a very valuable law. A 2 kilogram load is hung from the end of a spring. The spring is stretches at a distance of 10 centimeters. So there's my spring. And there it is to begin with. And, there it is to, well, I can't do that, can I? Well, here's the spring to begin with, without having anything on it. And here's the spring. This is the before, and this is the after. And this has been stretched a little bit. And it's been stretched by 10 centimeters. Again, this is 2 kilograms, so this is going to be 2 kilograms. The spring stretches by 10 centimeters. If instead you put 4 kilograms on there, how much would the string stretch by? What do you think? You double the load, so what do you think is going to happen to the stretch? What's your experience? If I pull on the spring twice as hard, what do you think I'm going to get for this extension of the spring? Think back about FR is equal to K times X. So we doubled FR. And K is all about the spring. It's like each spring has a value of K. It's how far it stretches for each Newton. I'm not changing that. It's the same spring. So if I double my FR, what do I do to my X? Double it, don't I? So it's going to be from 10, it goes to 20 centimeters. If a force of 10 newtons stretches a certain spring 4 centimeters, how much stretch will occur for an applied force of 15? So what do you think? Have I got that one? So have I got that one? So you go from 10 to 15, 1.5 times your force.
I found it. It was Monet.
Monet did that. He cut his eyeball.
It's because he had cataracts, and they did the surgery.
Yeah. I'm getting that.
So that was like right before the surgery, and that was right after.
That's amazing. So he got, because of the thing. That's amazing. I've got to look that up. Thank you. So what do you think? Let me just put this on briefly. So, let's stop that there. And what we're saying, mainly see, it's 1.5 times the force, so it's going to be 1.5 times the extension. So, nice and linear. Okay. Let's put this idea of stretchiness. I suppose I can also compress things. So springs can be stretched. A car spring can be compressed, yeah? If you get like a spring they tend to have in physics labs, they're pretty weak springs, and weak springs tend to run into themselves. So you can't compress a spring like that very much. But a stiff spring, you can stretch it and you can compress it. The atoms in a solid are separated by, the actual matter is separated by electrostatic forces which obey Hooke's law. So they can be stretched and they can be compressed. And that leads to some very interesting things, you see. So we say steel is a great elastic material. It takes about 70 stories, it takes about 70 stories, 70 floors to compress a steel column by 1 inch. So if you laid the girders out on the road sideways, they'd be 1 inch longer than when you put them on end if you have a 70-story building. 70-story building. So, okay, it's pretty good stuff. It's not perfectly rigid, but it's pretty good. When a girder is used horizontally, it actually experiences both a tension force, it's stretched along the bottom, and it's compressed along the top. And this is a poor diagram on my part, so I want to kind of point something out. That end should not be vertical. That end should be kind of sloping, so that you do get this idea that you got a bigger length along the bottom, and the only way you can get that is by stretching, and a smaller length along the top, and the only way you can get that is by compressing. In the middle, there's a bit which is just as long as it always was. So that's neither stretched nor compressed. So there's a neutral bit in the middle. The girder will, if the girder was to bend like that, then what's stopping it is the fact you're trying to compress the top layer and you're trying to stretch the bottom layer. So both of those two layers are very, very, very important. It's really the top layer saying, I don't want to be compressed, and the bottom layer saying, I don't want to be stretched, that gives that floor, that girder, its rigidity. Okay? The neutral layer doesn't do much. So then people started saying, you know what? The middle bit is just to keep the top away from the bottom and the bottom away from the top. So we can make a girder, not as a solid plank like you might do with wood in a small structure. We make an I-beam. So we actually have a big piece of wood at the top, and this piece of wood does not want to be compressed. And we have a big piece of wood at the bottom, and that piece of wood does not want to be stretched. And then we have what's called the web in between. And all the web does is it keeps the top up and the bottom down. It stops them from joining together. And it turns out the bigger the web, the actually stronger the structure is. So you make this thing strong by actually just having a strong bit at the top and a strong bit at the bottom, and then a skinny bit can keep them apart. And if you have an I-beam that's like that, and you compare it with an I-beam that's like that, this is going to be a stronger I-beam than that one is. Even though the top materials are the same, and even though the bottom materials are the same. It's just better. And an I-beam like that is actually, in terms of density and weight and strength, is actually better than a solid piece of material. Well,
What is a story defined as?
pardon? A story is a floor. It's like a floor. Like a 100-story building is a 100-floor building. So steel beams have I shape because they don't need so much material in the neutral layer. You need it in the compression and tension layers. And what that means is if you want, you can run your plumbing through that bit. And it doesn't do much damage. But if you put your plumbing through there, if you actually split the top bit, you've destroyed your girder. It's nowhere near as strong. So it's actually really useful. And even with wooden beams, they use basically engineered beams in houses and the like. And they'll be wood, but they'll be shaped like this I-beam. They'll be like that. And you're supposed to run all your plumbing through there so that you don't compromise the integrity of your house. I bought our house, me and my wife bought our house maybe 8 years ago. And the inspector came to inspect the house. If you ever buy a house, be there when the inspector's there. The inspector works for the bank. The inspector's there to make sure you don't buy a house that has huge problems, because the bank is lending you the money. And if the house falls down, the bank's stuck, you know? So they're looking after their investment. So they don't work for you. You pay for them, but they don't work for you. They work for the bank. And my realtor said, you got to be there when the inspector's there. And I said, why? And she said, because if he sees a problem that's small and you're there, he may just make you promise to fix it. But if he sees a problem that's small and you're not there, he really has to put it down, and the bank then gets involved saying, we're not giving you a mortgage. So, for instance, I had a drip in one of my bathrooms, and the inspector said, you got to fix the drip. You promised me you're going to fix the drip. And I said, yes. And he looked in the ceiling and he said, there's not enough insulation in that ceiling. Are you going to put insulation in? I said, yes, you know. Otherwise, he'd have said no, and I'd have had to go to the seller and said, you got to put the insulation in, and we've got to go through this whole process again. And it would have been a real hassle. So I used the same inspector when I bought my second house. And this inspector, he was a very nice guy. He remembered me. I remembered him. He was a decent fella. And everything's going smooth. And he goes into the attic above the garage, and he comes back, and the guy was white. He was ashen-faced. And he said, to the homeowner, I need to talk to you. And he said to me, you need to listen to this. And he said to the homeowner, you have cut out the beams, the girders, the supports in the attic above the garage. And there's no way you can sell that house while it's in this state because it's structurally unsafe. And the guy said, I was wondering if you're going to catch that. He said, we wanted more storage, so we decided to put it above the attic. And the guy said, you're going to have to employ an engineer to fix it, and it's going to have to be signed off. And so our house sale was held up by this. But the guy had basically cut through, wooden beams like this because they were in his way when he was walking around. And man, it was so dangerous, It could have been so bad. So be careful. If somebody wants to run a pipe through your attic, make sure they do it in the right place. This ability to be able to make stronger materials and different materials really affects design. So if you look at some of the old structures, like the old temples in Egypt, they have lots of column and relatively little walking space. They have these big, massive columns. They look very grand, but they're needed because you've got to hold the roof up. You can't have a big, wide expanse of flat roof when it's made out of stone, because what happens is stone is really good in compression, but not in stretching. If you want to crack a stone, you hit it with a hammer, and you hit it with a hammer when it's over a gap. You don't put it on another stone and hit it. It's not so good. You put two stones on either end and you hit it, and then it breaks. Because that tension bit means that cracks can propagate really well. Well, that's a problem. The weight of the actual stone can cause it to crack. So if you have a big stone roof, you put lots of columns in there. So you get a lot of column and relatively little room. Same thing with mines, actually, with coal mines. When you dig a coal mine, they have to leave an awful lot of the coal in the coal mine because they can't take the entire seam out because the roof will collapse. So they actually have these quite narrow bits where they're taking the coal out, and then these big columns left inside of coal that they could use. In some cases, they can jack the roof up and take the coal out and then move on, but the roof is collapsing behind them. Now imagine, that's not a kind of job that I'd like, where I'm digging something out and then the mountain is collapsing behind me as I move forward. It's not particularly good. But that's what happens when you have a flat roof. There's not much you can do about it. Well, there is something. You can invent the domed roof. So what happens this is, by having a dome, you have compression on both sides. If you think about it, this is trying to get to a lower state, which is less long, which is compression. When this thing stretches, it goes to a bigger line, and so that's stretching, which is tension. Can you see the difference? So this guy, because the mode of failure is to fall, it goes to a smaller arc, and therefore, as it falls, it's compressing. Stone is very good in compression. So we say stones break more easily in tension than compression. So in old buildings, the columns are close together because they can't stand a big span. They'll just crack. Arches allow columns to be separated by greater distance because the mechanism of failure, the mechanism of really stability, involves compression on the underside as well as on the top side. So it's really quite strong. When you walk on floorboards that sag due to your weight, where is the neutral there? Is it on the top surface of the floorboard? Is it on the bottom surface of the floorboard? Or is it in the middle? Where is the neutral zone? What do you think? Is it the top surface? Is it the bottom surface? Or is it in the middle? Where do you think? And I'll stop this in a minute. And it's going to be, stop there. And it's going to be, let's have a look. Yeah, it's going to be in the middle. That's where the neutral zone is. So that's that guy. And then, if you must drill a horizontal hole through a tree branch, here's the tree branch, and you want to drill a hole through it, would you do it in the top, or would you do it in the bottom, or would you do it in the middle? You'd do it in the middle. Okay, because it's the neutral zone again for a tree branch. It's supporting its own weight. Compression underneath, stretching on top, neutral zones in the middle. Is it easier to break a cup by hitting the outside or the inside? So here's a cup. If I want to break it, is it better to hit it there, or is it better to hit it there? Which would it be best to hit it? A or B? It's going to be on the outside, isn't it? It's better to do that. I wouldn't have thought about that. It's like, it's like it comes out of this. Okay. This next bit is kind of amazing. I'm not going to dwell on it too long, but it is kind of amazing. 1950s, horror movies. There was this whole spate of horror movies about a nuclear test that went wrong and monsters were created. Spiders as big as houses is the one that I remember best. And so you'd have this trailer, and have like the house, and then they have what's clearly just a spider, like photographed, and the spider is like walking all over the thing, and then it cuts to people screaming, okay. Physics point of view, total nonsense. And the reason why it's total nonsense is because you've got to take scale into account. And you can't just make something 3 times as big and have it behave the same way. So you've got to deal with dimensions. And there's 3 dimensions. There's a 1-dimensional thing like a length. There's a 2-dimensional thing like an area. And a 3-dimensional thing like a volume. And they're as simple as that. So you can think about potatoes, or you can think about spiders, or you can think about whatever you like. But they'll behave just like a cube in terms of their scaling properties. So if I take a line that's 1 unit long, and if I double it, then the new line is 2 units long, and if I triple it, the new line is 3 units long. The diagrams are not that great, but you get the idea, yeah? If I make this line 3 times bigger, it's 3 times as long. If I make this line 2 times bigger, it's 2 times as long. If I make it half as big, it's half as long, yeah? What about area? Take a square. If I make this thing twice as big, what does that mean? It means the linear bit is twice as long. If I make this thing twice as big, then it's got 1, 2, 3, 4 times the surface area. So what that means is if I make a spider that's twice as tall, twice as wide, and twice as deep, no matter what its shape, as long as it keeps the same shape, the new one will be 4 times the surface area of the old one. You don't have to figure out the detail. It's dimensionally twice as wide, twice as high, twice as deep. The surface area is 4 times as big, no matter what the shape was, as long as it stays the same shape. Spider looks like spider. Person looks like person. The volume, oh my word, now we have, well, it's twice as wide, twice as high, twice as deep. So if I draw it and imagine making it out of sugar cubes, then I have 1, 2, 3, 4 sugar cubes on the top, and 1, 2, 3, 4 sugar cubes on the bottom. That's 8 sugar cubes. So this 1 cube becomes 8. So you get 8 times the volume. If I 2 times the length, I get 8 times the volume. I get 4 times the area. And that's what you learn. 3 times the length, 9 times the area. 3 times 3 times 3. 27 times the volume. 5 times the length, 10 times the area. Oh no, 5 times 5. 25 times the area. And then 5 times 5 times 5. 125 times the volume. So you take whatever the dimensional change is and you square it for the area and you cube it for the volume. Okay, and that's what I'm trying to show in this diagram. So we say if you double the size of a block, that means 2 times the length, so that means 2 times its width and 2 times its height. Well, it's 2 times the length, which means 4 times the surface area and 8 times the volume. So this actually tells you about some really interesting stuff. Like, for instance, I'm not a biologist, but if a cell is such a valuable design, biological design, why don't I drive down the road and see this huge cell the size of a house? If it's that amazing a structure, why don't I just have a really big one? And the answer is that it's all about dimensions. If I take doesn't matter the shape, if I take an object, a cell, and I make it twice as big, what have I done to its volume? I made the width twice as big, I made the height twice as big, I made the depth twice as big. Think back about the cube, it's the same answer. What did I do to the volume? Let's go back. When I made that cube twice as big, that means twice as wide, twice as high, and twice as deep. What did that do to the volume? I went from 1 sugar cube to how many sugar cubes? 1, 2, 3, 4, 5, 6, 7, and 8's at the back, and you can't see, yeah? Yeah? So I have 8 times the volume when I make the length twice as big. So I have 8 times the volume when I make the length twice as big. Same shape, so it works, yeah? You got to feed the inside of a cell. It's a little animal. It wants energy, it wants food. If I have 8 times the volume, I have 8 times the need for food on average. Yeah? If I have 8 times the need for food, I have 8 times the hunger. Now, how does a cell feed? It absorbs through its skin. It's not got a mouth, it just absorbs through its skin. If I make the cell twice as big, that means twice as wide, twice as high, twice as deep. Thinking back about the cube, what have I done about its surface area? 4 times as much. So, I'm 8 times as hungry, but I got 4 times the ability to eat. That doesn't work out. If I'm 3 times as big, I have 27 times the hunger and only 9 times the ability to eat. If I'm 10 times bigger, I have 1,000 times the hunger, but only 100 times the ability to eat. So I starve. It's like I'm going to get, if I got a cell the size of a building, it couldn't feed itself. It would starve to death. So what does it do? It breaks into 2. Same volume, more surface area. So it's enabled itself to feed. So cells get to a certain size and then they divide because they can't feed themselves. So that's like a good justification for cells dividing. I'm just looking at this, I don't want to run out of time. If an animal's linear dimension is doubled, its cross-sectional area is 4 times bigger. Its volume is 8 times greater, so its air resistance is 4 times bigger, because air resistance depends upon area. There's the wind going by you. And its weight is 8 times bigger. So what happens is bigger animals tend to plunge faster. So if I jump off a building, I will break my legs. But you take a little mouse, and because it's so much smaller than I am, it kind of floats down. Don't try this, don't get a mouse and do it, but it kind of floats down and it scampers away. And then cooking, when I saw my wife, I'm going to stop this for a minute. So what we're going to do is we're going to turn around and say, if we imagine a 1 by 1 centimeter cube, and we so here are some problems. We're basically just going through and saying I have a 1 by 1 by 1 cube, and if I double its size, what do I do to its length of side? Well, it's just going to be twice as big. And what would I do to the area? Well, it would be 2 times 2, which would be 4 times as big surface area. And what do I do to the volume? That would be 2 times 2 times 2, which is 8 times the volume. And then, well, what about things that, scale proportionately? So what about mass? Well, mass depends on volume. So that, again, if you had something that was 2 times high, 2 times wide, 2 times tall, and 2 times deep, it would be 8 times the volume, so it would have 8 times the mass. And what about something like weight? Well, weight is mass times acceleration, that times the gravitational field strength. So it would be 8 times the gravitational field strength. And you can do the same thing for these examples. Twice your size. How would your height change? Your height would be twice as great. What about your strength? Well, your strength depends upon the cross-sectional area of your muscle. So that's an area, so it's 4 times as big. And what about your weight? Well, weight depends on volume, so it would be 8 times as big. And that's it. So there we have it. I'm sorry I didn't record these last questions when I went through them in class, so I just did it very briefly now. Thank you.